This lesson will focus on waves and mainly looking at the properties of waves. So this should be hopefully a little bit of a review from you from last year, so this should be easy, so I will breeze through this relatively quickly. Alright, so what is a wave? Well, if you think of it, there's really the study of physics is all about energy and the transfer of energy from one spot to the next. So a wave is simply a transfer of energy from one spot to another. Okay, we can really transfer energy in two ways. The first way is to just physically move something. Okay, you can throw an object from one spot to the next. You are transporting energy with that object to a different spot. Or the other way in which you can transfer energy is by sending waves. So it's just another way of sending energy from one spot to the next. Okay, there's really two main categories of waves. The first is a mechanical wave. Mechanical wave is one that requires a medium to travel through. And then an electromagnetic wave. An electromagnetic wave does not require a medium to travel through. Okay, an electromagnetic wave would be something like light, microwaves, gamma rays, all those kind of that. Last year, if you remember, we talked about the electromagnetic spectrum. All those deal with light waves. Okay. Now, looking at these two, one requires a medium, one does not require a medium. So, what is a medium? Okay, well, a medium is defined as a substance, usually matters, could be a gas, could be liquid, could be solid, through which energy is transferred. Okay, so that is a medium. So a mechanical wave requires air, requires a liquid, requires a solid to travel through. Electromagnetic waves do not. Okay, that is why, if you think of in space, mechanical waves cannot travel through space. Electromagnetic waves can. That's why we get sunlight from the sun, right? Because the light is able to travel through empty space and get to Earth. Alright, so now we're going to look at the different types of waves, and we're mainly in this unit going to focus on mechanical waves. So basically a wave is created by a disturbance. Okay? Now if we create a single disturbance, what we get is something called a wave pulse, which is simply, I'm sure you guys have a background knowledge on what a wave is. A wave pulse is simply half of a wave. Okay, a wave would be full disturbance up and down around that equilibrium point. A single disturbance is just half of that. Okay, so a disturbance up or it could be a disturbance down. Okay, that disturbance travels through the medium. We'll find the next lesson will be on wave speed. You'll find that all waves travel at a constant speed. And notice again, like I said, it's not a complete wave, so that is a wave pulse. Alright, now there are really two types of mechanical waves, and before we go through that, where are these waves? What is really the product of these waves? Not the product, but what is the cause of these waves? Okay, back in when we talked about torque and those things, we looked at something called simple harmonic motion. Okay, mainly we looked at two different types. We looked at a pendulum or a mass spring system. Okay, so consider, let's say, a mass spring system. So here's a spring with a mass. If I disturb this mass, okay, it's initially at some point that we call equilibrium. Okay, if I disturb this mass upward, what's going to happen is it's going to oscillate up and down across this equilibrium position. Okay, and that oscillation is repetitive. It's going to continue on and on and on. And if there is no friction or anything, any non-conservative forces present, that disturbance is going to continue on and on and on. So that constant repetition basically is what creates a wave. Okay, same thing with a pendulum. A pendulum, you lift up a mass to some height, and that mass is going to oscillate between two positions, always crossing some equilibrium position. Okay, so it's always going to go back and forth. So it's a repetitive oscillation. Just like think of what we just talked about, a wave pulse. A wave pulse is created by a disturbance. Waves, a full, complete wave is still a product of a disturbance. In this case, the disturbance is simple harmonic motion, or repetitive disturbance. Okay, so that's kind of the cause of really all types of waves, either mechanical or electromagnetic. But now we're really focusing on mechanical waves. Remember that require a medium. Okay, so there are two types of mechanical waves. The first one is a transverse wave. Okay, a transverse wave. So that transverse wave is where the disturbance oscillates perpendicular to the direction of the wave. Okay, we'll look at that in a second. And then the longitudinal wave is when the disturbance oscillates parallel to the direction of the wave. Okay, so in a transverse wave, what we said is that particles vibrate perpendicular to the wave direction. Okay, an example of this would be like the mass spring system I just talked about. Okay, so if you consider the spring and the mass, okay, it's going to oscillate up and down. Now, if you remember back to simple harmonic motion, all right, if we were to graph this repetitive motion over time, what you'll see is that this wave pattern will look almost like a sine curve. Okay, notice that the wave is traveling from left to right. I'll label that as V, that's its motion. And notice that the particles are oscillating. If this is equilibrium, particles are or this mass would be vibrating perpendicular. It's going to go up to some maximum positive amplitude and then down to some negative amplitude. Okay, so it's vibrating up and down while the wave is moving from left to right. So there's perpendicular 90-degree angle. All right, characteristics of a transverse wave. Notice again it has areas of maximum positive displacement and negative displacement. So again, about equilibrium, if I draw equilibrium here, what we call this positive displacement here is a crest. Okay, and the negative displacement is what we call a trough. Okay, so crests and troughs are associated with transverse waves, and it's just the areas of maximum displacement, whether positive or negative. And like I said before, this motion, if you look at it, really is represented by a sine curve. Okay, and if you recall back from early chapter 13, we can take this type of motion and graph it, and we looked at, specifically with chapter 7 and chapter 8, we looked at angular velocity represented by omega. Okay, where omega was equal to 2 pi times f, which f is the frequency. And this function here, x of t equals a, which is the amplitude, times the sine of 2 pi ft, represents the position of a wave in terms of time. Okay, then taking the derivative of that gives us the velocity of this curve. So the velocity is kind of the same function, but now instead of a sine, it's represented by a cosine. Okay, remember where you have spots of maximum displacement, where you have a maximum amplitude, your velocity is equal to 0. Okay, where your amplitude is 0, your velocity is maximum. Okay, so here at that point you'd have maximum velocity, and here you would have 0 velocity where you have maximum amplitude. Okay, so just kind of some things we've already talked about in terms of waves. Alright, now some of the properties of waves that we'll talk about, and this deals with both transverse and longitudinal waves. Okay, and this is kind of a review again. So I've already kind of mentioned it, but the amplitude here, maximum displacement from equilibrium, measured in meters. Frequency is the number of waves past a given point in 1 second. So it's really waves, or it could be oscillations, whatever, per unit of time. Okay, so waves per time, which is waves per second, which we give units of hertz. Okay, so it's units of hertz. Again, this should hopefully be a little bit of a review. But it's the frequency, the number of waves in a given second. Okay, and then flipping that around, when you look at the time per wave, we call that the period, the amount of time it takes to complete one cycle or one complete wave. One complete wave in terms of transverse would be a full crest and a trough. Okay, and then recall the relationship between period and frequency is that they're inversely related. If you notice the units, waves over time, so waves over time, time over waves, and that gives you kind of that inverse relationship. Alright, so just kind of go back and refresh your minds on the properties. Alright, so here's kind of an example of just recognizing these things. Say the amplitude here, notice the wave maximum displacement, the amplitude shown in meters here, in centimeters, amplitude would be 2 centimeters. The period, we're looking at one full complete wave. So remember, a simple crest would be just a pulse. Now looking at a crest plus a trough, that's an entire wave. Starting at 0, we go to 4 seconds, so our period would be 4 seconds. And then frequency, number of waves per second, well, if you look, you can either use the graph. Here's 1 second. Well, how many parts of a wave do you have? while looking at it, you have, by shading this region, 1 part, 2 parts, 3 parts, 4, right? So in 1 second, I am only looking at 1/4 of that wave, shown here, so 0.25 hertz. Going and calculating it again, frequency is equal to 1 over the period. So if my period is 4 seconds, simply get a frequency of 0.25 hertz. Okay, so it's just kind of understanding these relationships again. Alright, now longitudinal waves, different from transverse waves. Now in longitudinal waves, the particles are going to vibrate parallel to the direction of the wave. Okay, so if the direction of the wave is going to the right, the particles are going to oscillate back and forth across some equilibrium in the same, either in the same direction as the velocity, okay, either in the same direction or kind of opposite the motion. All right. So you get, is obviously a lot different than a transverse wave. And the characteristics of a longitudinal wave is you get 2 points. Similar to a crest and a trough, you get points of maximum positive amplitude and negative amplitude, just like a crest and a trough. And what we call those are a compression and a rarefaction. Okay? Now, this kind of talks about what we've been dealing with the last couple units, is that if you think of a compression and a rarefaction, another way of talking about a longitudinal wave is a pressure wave or a density wave. Think about this. A compression is where you have positions where a lot of particles, think of compression with chapter 12, you have a lot of particles that are close together. So compression is a point of high density. Okay? So here's what we call a density wave. So you get a lot of particles that are close together. Think pressure, when a lot of particles are close together, right? They don't want to be that close together. They get all jacked up, right? So these, where you have a compression, you also have increased pressure, and I guess you also have increased density. Okay? And in a rarefaction, you have the opposite. You have low pressure, low density. Okay? The particles are not close to each other. So what happens is, say, take a particle right here. What this particle will do, if the wave is traveling to the right, this particle is going to oscillate back and forth from right to left. Okay? And it's going to switch from going to a compression to a rarefaction. The particles are basically going to go back and forth, and you're going to get this variation of pressure that's going to travel through this medium. Okay? Primary example of a longitudinal wave is sound. Sound is what's called a pressure or density wave. Okay? When you speak, basically you are making the air molecules kind of collide with each other. That collision will create that pressure variation, and that pressure variation will travel from one point to the next. And usually it'll hit your ear then, that vibration will hit your ear, vibrate your eardrum, and that'll get transmitted to your brain as sound. And we will look at sound as part of this unit. Okay, and then also transverse waves are obvious to see that you get a sine curve. Now, a longitudinal wave is different because you have the points of compression and the points of rarefaction. So how does that represent as a sine wave? Well, if you talk about a compression, is what I said was where you get increased pressure or increased density, right? So think of that as kind of a maximum amplitude. So a compression would be represented as a kind of a crest. So here we could see a compression, all right? And the rarefactions are points of low pressure and low density. So it's the opposite, where you have a kind of be your maximum negative amplitude. That would be what is called your rarefaction. So we can also represent these as a sine curve. Okay. And then kind of the last property of the wave that I would like to talk about today is the wavelength. And we didn't specifically talk about this in chapter 8 or 13, but wavelength is simply, you think of the word, the wavelength, the length, okay, the length of one wave. Okay, so how do we measure that? Well, the wavelength is really just the distance between two successive points. Okay, so an example of that would be a crest to crest. Basically, you're taking one point on a wave and you're going to look at that same point on the next wave. Remember, a wave is a complete crest. So if this is equilibrium, it's a crest and a trough. So this is one wave. Let's say I look at this point here. Oops, there we go. That point there. Okay, this is one wave. The next wave would be this one here. So it doesn't necessarily always have to be crest to crest, but it's the same point on successive waves, so waves that are next to each other. So if my first point was here, then this is kind of the end of the first wave. The next wave starts, it'd be the same point. The distance between those 2 points is known as the wavelength. And we symbolize this with the Greek letter lambda. Hopefully that's spelled correctly. And it's pretty simple. We're measuring it in meters, and really the units are meters per wave, but we're just going to drop the wave and just simply look at meters. Okay. So down here in this diagram, it's kind of showing just on this would be a transverse wave. That one's pretty easy to see. Again, wavelength is not that difficult really to understand, but looking at this point to this point, full wave, and then we're looking at the next wave, the same point. Then you can also look at wavelength and a longitudinal wave. Is that where if you say you look at a compression, you're going to look at the next compression, and that's going to represent, okay, a wave. Because here you would have, looking at like a sine curve, you would have a crest, a trough, and crest. Okay, so it would be like a crest to crest again. Okay, so wavelength is just the distance between 2 waves. Okay, now using these properties, our next lesson is going to focus on wave speed. So kind of take a look, refresh your minds with these things, maybe go back and look back at the early parts of chapter 13 with simple harmonic motion, because those things could be brought back now into this new unit on waves.